There you go.
Okay. So first of all, I would like to thank the organizers a lot for the invitation to give this hands-on session. And yeah, today we will. So this is the first time I actually do a tutorial on micrOMEGAS, and even more so, an online tutorial on micrOMEGAS. So I hope I have timed things more or less correctly. And yeah, whoops. Yeah. So this is what I will be talking about, as you also probably saw in the preparatory instructions that were put on the school webpage. So first of all, the first part will be a little bit of a more classic talk in the sense of looking a bit historically how micrOMEGAS came to be and what it actually is. And then we will, for the three remaining parts, we will delve into the various steps of the process of moving from the level of a Lagrangian that we have in our heads to implementing this Lagrangian into micrOMEGAS and doing some terminology with the program. So I already said that micrOMEGAS is a program, of course, and we'll go on to say a few more things about that. So for some reason, my arrow keys are not working. Okay, so let's start with a bit of history. So in the early 2000s, if you wanted to compute the dark matter abundance predicted by your favorite model, you had to follow a series of steps, which are pretty logical, actually, and make quite a bit of sense. So we had, of course, to conceive and write down your Lagrangian, to extract all the vertices, to figure out which processes are relevant for dark matter production and dark matter depletion. Then you had to compute all your cross sections, write down your Boltzmann equations, and at the very end, and this was an extremely tedious part, code all these expressions and numerically solve your Boltzmann equations. Now, how complicated is this series of steps? To be honest, I was not in research at the time. I'm a tiny bit younger, but to me, it sounds pretty complicated overall. And to get a sense of exactly how complicated this can become, it's interesting to recall that at the time, supersymmetry was still the most popular type of extension of the standard model. And so if you just consider the minimal supersymmetric extension of the standard model, let's write down a little bit what it involves to calculate, for instance, the neutralino relic density. So in the MSSM, you have 28 BSM particles plus 17 come from the standard model. All of them can, in principle, annihilate and co-annihilate, either with the dark matter candidate or among them. And if you actually do the counting, and people at the time did the counting, this amounts to more than 2,800 processes. Truth be told, in principle, not all of them are relevant usually, but still, first of all, I can always imagine a very weird scenario in which all 2,800 processes are relevant. But even if you start eliminating processes by putting particles to be heavier and so on and so forth, it is still a lot of work to write down all of these processes and code all of these processes. However, people did do it at the time, and they even developed public codes to numerically solve the resulting Boltzmann equations. One of the people you will also get that did this, you will also get to talk in tomorrow's tutorial on Dark Suzy. But a common feature of all the codes, all the public codes that existed at the time, is that all the relevant expressions, all the cross sections, all the Boltzmann equations were hard-coded. So they were written specifically for the MSSM. And this means that this procedure had to be repeated for every new model that you had that you conceived. So if from the MSSM you went to the NMSSM, you had to repeat the whole process. Of course, you could inherit a lot from what you had done from the MSSM, but keep in mind the NMSSM is an even more extended model. And as usual, the idea of automatizing some steps of this procedure arose. So if we take our list of tasks in order to calculate the relic abundance of dark matter in our model, the last 4 steps tend to be the most time-consuming. So figuring out which processes are relevant for dark matter production and depletion, computing all the cross sections, and here computing, we mean computing more or less by hand, writing down the relevant Boltzmann equations and coding these expressions and numerically solving these Boltzmann equations. So these 4 steps are probably the most time consuming. And what is also extremely important, they are the most prone to human error. I mean, of course, they extract all the vertices. It is also prone to human error because everyone always misses a factor 2 or a factor I every now and then. But these 4 steps are really, I mean, if you have to code 2,800 processes and compute the cross section, so on and so forth, it is highly likely that you might make a little mistake or a minus sign or something like that. Of course, today, some of these steps can be automated using different tools. For instance, you can use MatGraph if you're going to calculate your cross sections, so on and so forth. But keep in mind that we're talking about the early 2000s. So at the time, these tools either didn't exist, or if they existed, they were less developed. And secondly, you still need to do quite a bit of work if you want to bring all of these pieces together. So you will get your cross sections in on one side, and then you have to transport all that, incorporate those in your Boltzmann equations, and then write your solver in order to solve the Boltzmann equation. So can we make our lives a bit easier? And this was the original idea behind the first version of micrOMEGAs. And actually have the pleasure to have one of the original authors of micrOMEGAs, Geneviève Bélanger, here among the audience, who accepted kindly to be present during this lecture so that she can also correct me if I say things which are inaccurate and or false. So the original idea behind micrOMEGAs was that once a particle content and the interactions between these particles are specified, the rest can be automated. And in particular, what can be automated is figuring out which processes are relevant for dark matter production or depletion, computing all the cross sections, writing down the Boltzmann equations, and one of the most important parts, the coding of these expressions and the numerical solution of the Boltzmann equations. This is what gave rise to the first version of micrOMEGAs, and which is a program was at the time a program to calculate the relic density in the minimal supersymmetric standard model. Keep in mind that all cross sections are computed at tree level with an external somehow programming. It's incorporated in micrOMEGAs, which is called CalcHep. So what is micrOMEGAs? In one sentence, micrOMEGAs is a computer program which is written in C for the automatic computation of dark matter observables in generic extensions of the standard model. It can do many things, compute the predicted dark matter abundance in a user-defined model according to the freeze-out or freeze-in pictures, including, by the way, as of relatively recently, 2-component dark matter scenarios, since a few years, actually. It can compute observables for direct detection of dark matter and indirect detection of dark matter under varying astrophysical assumptions. So you can play around with the astrophysical assumptions. It can compute decay widths and cross sections, for instance, for collider analysis. If you want to check, for instance, if your model is violating Z or Higgs bounds into invisible, or if it is violating this or that LHC bound from some whichever cert channel you're interested in. For some models, for instance, the MSSM or the NMSSM, it can compute additional observables such as B to S gamma. These are not generic features. They are a little bit more model dependent. And it can interface, it comes with interfaces to other phenomenological pieces of software, such as models, which is used in collider analysis, Higgs bounds to test your Higgs sector. It can be used to plot useful quantities and so on. The current version of the program is micrOMEGAs 5, which came out about 3 years ago now. And yeah, so how to use micrOMEGAs in a few sentences. The basic steps to follow if you want to use micrOMEGAs to compute observables for your dark matter model are 4, basically. So you need to write down your Lagrangian, and we will see what it means to write down your Lagrangian. You extract all the vertices and code them in an appropriate form. So this is the part where if you want to stick to just micrOMEGAs, this is your starting point. You write down what are your particles and what are your vertices. You edit the script in C, a main file, which we will see in the following, and then you just have fun. Now, the part of actually coding all the vertices can be a little bit tedious too, because you have to really write down all possible combinations of particles. I mean, the usual Feynman-Malur extraction from a Lagrangian. Of course, it's something that any particle physicist can do, but it can be a bit tedious, and it is also prone to human error. So the task of actually writing down the Feynman rules has also been automated thanks to external programs. I am mentioning 3 of them here. I assume there might be more. So LANHEB, Feynman rules, or SARA. And so the procedure essentially gets modified in practice as follows. So first you write down your Lagrangian, encode the Lagrangian in some appropriate form, some usually fairly compact form. We will see what it looks like. Then you generate your CalcHEP model files, which, remember, is the program upon which micrOMEGAS relies for the computation of all matrix elements and cross sections. And you import those files in micrOMEGAS. And this generation is done automatically by the programs that are used in the first step. And then again, you edit your main file, your micrOMEGAS main file, and you can calculate all the wonderful things that the program can calculate for you. If you wanna, I mean, today we will see a little bit, a few things about Feynman rules. If you wanna find out more information on LANHEB, Feynman rules, or SARA, I am writing down their websites here. And of course, you can, by all means, go through the very extensive and very detailed manuals of these programs. And the goal of this session is to go through all of these steps together, at least briefly. We will not have, of course, time to go through all the details, but at least the essential steps. So let's start with the implementation of a new model. And I'd like to point out that, strictly speaking, this is not yet micrOMEGAS. So we will only get in micrOMEGAS in the next step, which is importing a new model file in the program. So remember, the first step was writing it down your Lagrangian and coding it in an appropriate form. I will be using as an example the simplest model that I can think of, which is singlet scalar dark matter. This is an extension of the standard model. I think you must have seen this model probably in Genevieve's lecture a little bit earlier. So you extend the standard model by a scalar field S, which is odd under a discrete Z2 symmetry, and all the standard model particles are even under the symmetry. Under these restrictions from Z2, the most general Lagrangian you can write down is this one. So you have the standard model Lagrangian, a kinetic term for S, a bare mass term for S, a quartic coupling for S, and what is called a Higgs portal term, which goes like S square H dagger H. Now, once electroweak symmetry is broken, S can interact, and I'm only here counting 3-level interactions and maximum 2-to-2 interactions, either in pairs with a single Higgs boson, and this corresponds to an SSH vertex, or in pairs with a pair of Higgs boson. So the Z2, as usual, imposes that S interacts only in pairs. And in order to use micrOMEGAS, you would need to specify in the CalcHEP format the nature of the particles in the model. So, for instance, that you have the up quark and S and the Higgs boson and so on and so forth. So how many particles, their names, their spins, and their Z2 charges, and how they interact with each other, the vertices. This is where, I mean, of course, you can do this by directly writing down this information in the CalcHEP format, and we'll see what this looks like in the second part of in step 2, let's say. But thankfully, there is a simple way, which is by using model file generators. So programs such as LANHEB, Feynman rules, or SARA allow us to specify a particle content and input a Lagrangian in a way which is fairly close to what we would write in a paper, and give us as an output the corresponding information that is needed, for instance, by CalcHEP and micrOMEGAS in an appropriate format, so what we call a model file. I am mentioning 3 programs here. Each of these programs has vices and virtues. They can typically do much more than what we will see today. So today we're using them only in order to generate a model file. They can actually generate other types of model files for MatGraph, what else, for fine arts, and so on. And for more information, I really invite you to check their web pages and their manuals, which I gave a few slides before. Examples of what they can do is to generate counter terms if you're doing one-loop calculations. This is especially the case for LANHEB. which, by the way, is also included by default in micrOMEGA. So I am not 100% right when I say that we're not yet in micrOMEGA, since LANHEB is also included in micrOMEGAs, but in principle, it's also a standalone program. These programs can do all sorts of things: calculate and write numerical code for RGE running, compute decay widths, generate model files for math graphs, and so on and so forth. So in the end, which program you will use, for instance, if you want to generate model files for micrOMEGAs, really depends on taste, on what you find more convenient. We will be using fine rules, which is based on Mathematica. And I should say here that there is one weakness. I mean, this is just for my own personal convenience. It's the one that I know the best, and that's why today we'll see how this is done with fine rules. You can do the exact same thing with a procedure that is not that different using any of these programs. And on top, one nice feature, for instance, of LANHEB is that it does not rely on Mathematica. And there is a long and honorable tradition in high energy physics about using open source software. Today we'll be using a proprietary piece of software. But yeah, again, it's whatever each person prefers. So let's start little by little by writing down a fine rules model file for the single scalar dark matter models. Before we start looking at code, the model contains, let's see what is the particle content. The model contains one particle other than standard model, which is S, the scalar. The imposition of the Z2 symmetry restricts our Lagrangian. And as far as free parameters go, the model is fully described by three free parameters: the physical dark matter mass, the portal coupling, so this S squared H dagger H coupling, and the quartic coupling lambda S, which is kind of irrelevant for our purposes because it just takes two dark matter particles into two dark matter particles. There are situations in which this can become important if you have substantial self-interactions, but this is not something we'll be dealing with today. Whereas the bare parameter, please note, so this type of parameters, the parameters that we will be giving numerical values to, are called external parameters. And then there is an internal parameter, which is the parameter μs, which you can compute actually from the physical mass and lambda sh, and the Higgs web, of course. Note, of course, that the model also involves the standard model particles, Lagrangian, and parameters, which also need to be specified. So what does a fine rule? Let's start delving a little bit into the programs themselves. So some elements of a fine rules model file. One of the first things you will do is to declare your parameters. So parameter declaration fine rules, and in the other programs that I mentioned, it is relatively similar, resembles a bit like this. So here we have the bare mass term in mu SS. By the way, I'm calling S SS because unfortunately, otherwise there will be conflict with the S quark. So somehow you have to avoid such little mistakes when you write, and it can be very annoying the first time that you write a fine rules model file because you don't know what's going on and what's the matter. So yeah, SS here stands for our scalar S. And so you can declare the bare mass term mu SS. I mean, you can give it many attributes. It can have a tech representation. We take it to be real. It is an internal parameter. Here I can write down what its value is, and I can write a more human readable description for it. Note that this is a relation, its value, that I have to input myself. So a bit of offline work is required. Put differently, these programs allow you to do many things, but you do need to know how to write down Lagrangian, diagonalize mass terms, and so on and so forth. Okay. And this is an example of an external parameter. It's the S squared H dagger H coupling, where you see that in this case, the value is a concrete number, and it's declared as an external parameter. Interaction order is something related to math graph, which we will not be dealing with today. And there are actually more attributes that you can give to each parameter, but the general idea is more or less the same. A full list, of course, you can find in the fine rules manual. Then you have to declare your particles. So S is a scalar, and in the example of fine rules, scalars are declared as S and then a serial number, essentially. This is the sixth element of the list of scalars. You declare a class name. We take it to be a real field, so it's conjugate. It is not charged under SQ3 cross SQ2 cross U1, so it doesn't have quantum numbers. It has a mass. It has a width, which is in our case 0, since it is stable. A particle name, you can assign a PDG code if you want to it, and then attribute some other elements. What is important in our case is the particle name, whoops, which I have duplicated here. This is a mistake and I should have seen it. I'm sorry for that. What I will ask you to note is the tilde in front of their name, in front of the particle name. The tilde is completely crucial for micrOMEGAs. It is, I think, completely useless, for instance, for MATGRAPH or fine arts. But in micrOMEGAs, it is crucial because it allows the program. So when I go to extract my CalcHep micrOMEGAs model files, the tilde is what tells micrOMEGAs which particles are Z to odd, and hence are dark matter candidates. So for a particle to be considered a dark matter candidate, it must come with a tilde. It can also come with two tildes. If, for instance, I'm looking at two dark matter candidate models, I think there might have been a question. If there is a question, don't hesitate to interrupt me. Okay, no, I'm wrong. And finally, we have to write down our Lagrangian, of course. And this is what a Lagrangian looks like in the example of fine rules. So here I'm writing just the BSM part of the Lagrangian. So these are some Mathematica commands in order for II to be local variables and so on. You can declare conditions such as whether you're working Feynman or unitary gauge. And for instance, if you're not in Feynman gauge, then you set the Goldstones to zero. We have not seen how the Higgs doublet is declared. We will have a brief look right afterwards, because you can always write either in Feynman or in unitary gauge. And then you can see that the way your Lagrangian is written is actually quite close to what you would write on a piece of paper. So you have the kinetic term, then a bare mass term, a quartic term, a Higgs portal term where phi bar and phi, so this is H dagger H. There is Einstein summation assumed. And then you can also expand the indices of the SQ2 doublets. And of course, then you, depending on whether you work in Feynman gauge or not, you treat your Goldstones accordingly. And your total Lagrangian is the sum of the standard model Lagrangian and the new physics Lagrangian. So now let's have an actual look, because this is a tutorial and not just a talk. Let's have an actual look at our models. And I guess, I don't know if I should actually change my share screen or not. Yeah, I guess so. So I guess now you must be seeing my terminal. Yes?
Yes, we do.
Okay, great, thank you. So let's go in fine rules, models. And remember that I asked you to download a little zip file. So this is where we extract, this is where we write down our models in fine rules. Let's go in singlet scalar dark matter. And what you can see is that there is a series of files as well as a folder. So the main model files are, I mean, this is just the way I organize my, my model files. You can put the entire model in a single file or what you will. There is, I have separated the BSM part of the model and the standard model part of the model. In reality, to be completely honest, I have not separated the standard model part of the model. I have just stolen the standard model part of the model from the default fine rules standard model. So this is a nice, I mean, you can combine really models in order to write down your own extension of the standard model. So let's have a look at these model files. So let's open them. New share. So the BSM part, which I guess if I have changed successfully my share, but this is stuff that you can also look at locally. Okay, so we're looking at singlet scalar dm.fr. This is what it looks like. You can put down several comments and your name, the information of your model. In this case, I have set final gauge to false, so we will be working in unitary gauge. This I just left a little bit by default. It is something which is used by MapGraph 5. And then you can see, first of all, the list of our parameters. So in our case, we have the bare mass term. This is something which is needed by CalcHEP, actually. It's irrelevant. It's not part of the model, but yeah, I just included it for completeness. And then the quartic coupling of S, so the S to the 4 term, and the S squared H dagger H term. Underneath, I am declaring my particle classes, so my dark scalar. And then this is the Lagrangian that I just showed you. Okay. So now, where is the standard model? Let's go. So here I'm showing you the simple part. Then there is a standard model. So if you move to sm.fr, you can see what a much more complicated thing looks like. Okay, this is written in order to do everything that fine rules can do, actually. Very fast. I don't want to go into the details. Really, in order for this to be, yeah, one really needs to go a little bit through the manual. So you can define your gauge groups. The gauge group of the model is just the standard model gauge group. There is hypercharge left and color. Then various indices, which can be expanded or not expanded, and this is something that you choose. The interaction orders, and then you can declare your gauge bosons, which are go under V for vector. This is the photon, for instance. It is self-conjugate, it's massless, it is stable. The authors of fine rules chose to call it A, and so on and so forth. Then you have Z, W, the gluons. You can define your ghosts, because, of course, if you want to do, for instance, loop calculations, you need the ghost fields. These go under U. And then what is the most interesting feature, and this is one of the main things that these programs are extremely useful for, you can define let's say, your gauge eigenstates. So what we just saw for the vectors are the mass eigenstates, photons, Z, W, and so on. You can also define your gauge eigenstates, so B, the Wi's, the B and Wi's, basically. And then you can define what W1 is as a function of the mass eigenstates, W2 and W3, of course. Okay, so this is very convenient because this means that you can actually write down your Lagrangian in the gauge eigenstate basis, and then just through some replacement rules, obtain your model files into the mass eigenstate basis. Ghosts, for ghosts, it's the same, similar relations. Then we have the fermions. For instance, these are the leptons, the neutrinos. There are 3 neutrinos, of course, and they come with an index, which is, there are 3 neutrinos, and so the index is just a generation. This is the minimal standard model, so they're taken to be massless, they're stable, and so on and so forth. The charged leptons, ups, downs, and then you can define your unphysical fields, which are your left-handed leptons, your right-handed the right-handed leptons, and same for the quarks, up type and down type for the right-handed. And here's the Higgs underneath. If I'm going too fast, please do tell me that you're going too fast. Okay. And The authors of finals here are starting with the physical scalars. You see that this is the actual 125 GeV Higgs with its width and so on. And then there are the goldstones. And then you can write down your Lagrangian without needing to do the contractions yourself. Of course, these are easy contractions, but for more complicated situations, it's very convenient. You can define a Higgs doublet phi, which carries an SU2 doublet index. And then it has a hypercharge, which is 1/2, because keep in mind that finals will also check if you violate some charge. This is a part of a series of very simple consistency checks that is done. And you can define your upper component as a function of a goldstone and your down component after electroweak symmetry is broken. And it can be written as the VEV plus the Higgs boson plus the goldstone. These are some fine arts parameters. Okay, then you have a whole list of parameters. This is the inverse of the electromagnetic coupling and so on and so forth, the Fermi constant, etc., etc. This is not so interesting for our purposes. I will please ask you to go down to the bottom where you can find the Lagrangian. And so here, once again, you can see why these programs are pretty convenient. For instance, you can write down expressions which are quite simple, such as, this is the gauge kinetic part of Lagrangian, -1/4 field strength of B, field strength of B. So it is really, if you have defined your gauge groups and so on, fine rules and the other programs that you can use have internally defined what the field strength is. Or you can write down in the fermions part a little bit underneath this dCQL. This is the covariant derivative of the left-handed quarks. And the contractions are done automatically and so on and so forth. I mean, this is a more complicated, this requires a bit more complicated coding, of course, but you can use the standard model as an example to see how to build your own model. And at the end of the day, you can see that I am just adding a very simple part on top of the standard model that already exists. So now let's see. So far we have written the fine rules model file. Let's see how to extract model files how to generate model files for CalcHep. For this, I will ask you to open the file which is called load singlet scalar dm.nb. Oops. Okay. Let's share also my screen. Yeah. And so, okay, let's do some work ourselves a tiny bit. So let's run this notebook, but you need to modify it, of course, a little bit, because you will see that I have used as my fine rules path the directory where I have placed fine rules. So in this case, you have to change this path in order to match your own. And note that you have to repeat this a little bit underneath, once more underneath, where you load this restriction diagonal ckm.rst. So this restriction, yeah, we'll come to that. So I will wait 1 minute for everyone to change these paths to the appropriate path. Is there someone that has not done it so far? Okay. So, and what is done here is that we set a path, we load fine rules from this path, we set, okay, the directory, and then we load two models. We load the standard model and our singlet scalar extension. So you need to load them both, because you will remember that if you go back to your text editors where we're checking out the singlet scalar dm.fr, you will see that we have defined a total Lagrangian which contains LSM, the standard model Lagrangian, which is contained in sm.fr, and lnp, which is written just above this expression. So going back to my notebook, I can just run my notebook, and this will load. And load restriction is just, I mean, as the name of the file implies, this is just to say that, okay, ignore CKM mixing. Okay, so we take flavor diagonal interactions in the quarks. So let's run this. I hope it ran for everyone. Did it? If not, please do let me know. Okay, I assume that it has worked. And then you can actually do a lot of checks. I'm just exemplifying a few of these checks that you can do. So for instance, you can check that you have not messed something up when writing down expressions. So you saw that you can, in order to pass from gauge basis to mass basis, you can actually write down, you have to write down the expressions yourself. Then, I mean, this is a process which is still a bit prone to error. So there's a command which is called check mass spectrum. So of course it will it work? Yes. All mass terms are diagonal, which makes sense because this is the official standard model version, which is distributed by the authors of Fine Rule. So they took care very well of writing it properly. You can check if your Lagrangian is Hermitian. This is another basic consistency check. Let's see if it's Hermitian. Yay, it is.
Andreas,
Yes?
there is a question by someone in the chat
yes.
that asks you to repeat how to run the commands.
How to run the, sorry?
Commands.
The ones that I just run. Sorry, okay. Yes, I didn't say this. So in order to run some commands in Mathematica, you do Shift Enter.
Okay, I hope this answers the question.
Does it answer the question? Let's see. Let's look at the chat. Where's the chat? I cannot see the chat, I think. No, what's going on? Here. There are even more questions, actually. So Lorenzo, did you figure out how it's done? Okay, sorry. So what you need to do is, let's go through this again. I assume that since it cannot open Fine Rules, you have to modify the path that I have written down here, and which now should appear to be highlighted. This is a path that you don't think no, you think not. Okay, let's try to solve the problems that appear. If someone is it possible to share, for students to share their screens? Or is it just me that can actually share?
In principle, everyone can share, but maybe just one at a time, of course.
Yeah, of course. Yeah. So would someone want to share a screen? Someone for whom it's not working? For the question, is it possible to run it without Mathematica? It is not. This is one of the issues that I said, but so for this part, you will just follow what is going on, and then I have already generated the CalcHep model file, so then you will be able to join practically in the next part. So the I think not, I think went to the comment, is it possible to run it without Mathematica? Sorry, not to, yeah. So let me ask again, is everyone, does it work for everyone? I have run it on Mathematica Online, but there is an error. Mathematica Online, I guess, does not have the files that you are trying to, does not have your model files, I would assume. Yeah, okay. This you have uploaded. First of all, to Jennifer, downloading. So Mathematica, as I said, unfortunately, is not open source, and we are on live streaming, so I cannot recommend things which would be incriminating. So yeah, somehow, yeah, you'll have to find Mathematica. So Jigger has uploaded the files, and it's still not running, it would seem. Yes, please share the screen. Yes, sorry, I have to stop sharing.
You have to unshare before.
Yeah.
You are not able to share the screen?
Here we go. Okay, yeah, I mean, so you have not changed the path of the file that I said. So in the first line, this path corresponds to where the files are found on my computer. So somehow you need to modify this path for Mathematica to be able to find where you have put fine rules in your computer.
Okay, so there is a folder that I created and all the files are uploaded here. So is there any specific file that should be here?
No. Okay, let me show you. So I can tell you how my file structure is. Actually, you can see how my file structure. So you can see that, yeah. From the path here, you can see that my fine rules is in Dropbox, work, teaching, blah, blah, fine rules current, and this is the folder where I have put all the fine rules packages. So when you unpack, normally there should be a folder that's created that contains everything. So this is by default called fine rules - current, unless you called it something else.
Okay.
So if you modify this to be what you
and all the files are in the same folder and everything. Okay. So
do you have a terminal open?
Yes.
Is it possible? Would you mind showing the terminal?
Yeah.
So,
no, actually, all the files here on Mathematica Online is not accessed from here in terminal.
So the thing, I guess, is that you're using Mathematica Online, but Mathematica Online doesn't have, I think,
Access
a way.
to,
Yes,
yeah.
exactly. So I'm not sure if you can write. I think that in Mathematica Online, maybe you can write standalone notebooks. Perhaps I'm wrong about this because I've never used Mathematica Online. But it's not impossible that it can write standalone notebooks, but this is not a standalone notebook. It's a notebook that needs external files. So either there must be some way of uploading the entire package, so the fine rules current entire folder,
Okay.
and then finding a path, showing it a path for this folder.
That's what I did here. All the
That's what
42
you
files
did
are.
here.
Yeah.
Okay, so could it be, and you've actually put all of the files.
Yes, exactly. Yes.
So it cannot support file structure, folder structure, sorry.
Yeah.
And then this might be problematic because, so, I mean, as this is done on the fly, you know, we encounter issues that we have never encountered before. So I would think that it might be an issue that when you try to load fine rules, in practice, they should correspond to the finerules.m thing that you can see in locally in the finerules current folder. And then it has a specific folder structure in mind. So I'm afraid, without being 100% sure, that unless you can upload finerules current as such online and keep the folder structure, it's probably not possible to run the notebook.
Okay. Okay. So
Okay.
yeah.
So you need the local. I mean, the easiest, the cleanest thing to do is to have a local Mathematica installation.
Yeah.
If you don't, please be a little bit patient because this part will soon be over, and we'll go to the actual micrOMEGAs part, and then you don't need any proprietary software. If you've managed to make micrOMEGAs, you will be able to run everything.
Yeah. Okay.
Okay.
Yeah. Thank you.
Welcome. Anyone else who would like to say something since we're at it before I reshare my screen? That has encountered issues or something? Okay, probably not. So let's go briefly back to our to the notebook to get to the moment that we have all been waiting for, to write calcep output. Sorry, I have some question. In the installation, I have some warning, but I can run check mass spectrum. It should be normal, right? Can you paste the warning? And yes, Lorenzo is right that typically you can use a trial version of Mathematica for a few days. Yeah, so... okay, what you did is that you tried running, did you run twice? I'm talking to you, Grit. Did you try running twice the first commands? If yes, it's better to quit the kernel and then run again. In order to quit the kernel in Mathematica, you go to, shit, I've forgotten how to do it with the mouse. Wait, where is it? Evaluation, quit kernel, local. So, or you can run just quit. Yes, very good. And then you rerun your commands from the start. So it's a good idea at the top of every, so see, there's even quit at the top of my notebook, actually. Okay, great. Does it work now, Grit? Okay, great, welcome. So, and now let's run write calcep output. And now we have calcep model files. Okay, does everyone, I would like to ask everyone to go in the folder in finerules current, go to models, you're probably already there, singlet scalar DM already there, probably, then run ls and go to singlet scalar dm-ch. You should have 5 files in there. If not, either unmute and please say so, or send something in the chat so that we can pass on to the micrOMEGAs part.
We only see your Mathematica notebook, actually, Andreas.
Yes. Yeah. Okay. I didn't change the share. Let me change the share actually. So now you must be seeing my terminal.
Yes.
Okay. So as you can see, I'm in final rules current models singlet scalar dm/h. I run ls and I have 5 files with all ending with .mdl. These are the calcep module files that we will import in micrOMEGAs. Okay, if everyone has these files, since I'm not seeing any complaints in the chat or hearing any complaints, I will change my share to my slides again. So we will go back in the slides for a couple of minutes. Because now it's time for step 2, importing a model in micrOMEGAs. And so these are steps to follow in order to create a new project in micrOMEGAs. So let's go to our terminals again. You cannot see my terminal, but I assume that you can hear you can hear me. So please go. So normally you have all by now downloaded and installed micrOMEGAs. So let's go in the folder where this was done, micrOMEGAs _ 5.25.7.a. And the way to start the new model is by running the command that you can see on the slide, /new project, and let's call it, just for convenience, singlet scalar dm. Hopefully no complaints. And now, yes.
There is already a project of the same name. So like, will it rewrite that?
So the project that exists is called singlet dm. And I know that this exists. So a few models are implemented by default in micrOMEGAs, and this is actually the singlet scalar dark matter module. But I thought it would be a nice idea to go through the steps of actually starting from your Lagrangian and reaching down to micrOMEGAs. So yeah, let's create this new project called, let's call it singlet scalar dm. And so remember the MDL files that you saw that we generated a few minutes ago with fine rules? Or if you didn't manage to run fine rules, just please take these MDL files and place them in the folder that is on the slide, singlet scalar dm work models. Are we in sync? Is everyone ready? So I guess probably there are not so many problems. And so now the next thing that I would like to ask you to do is I'm asking you to go to one directory back to the work directory and run /calcep. And I think it's the best thing is to do is to share my terminal so that you can also see what I'm doing here. So once again, okay, let's run a clear because this is starting. Again, I am in micrOMEGAs singlet scalar DM work now, and I'm running /calcep. This should, okay, I do not know why I'm, here we go. So I will have a new share again. Unfortunately, you cannot see my, yeah. So do you see this gray box now? If you've run, sorry, I got X Windows not detected. CalCap has finished with error code 80. Okay, there is probably some incompatibility with the graphical interface of CalCap. Genevieve, have you got such an error message ever? This is something which I cannot answer actually on the fly.
No.
Okay.
It happens to me once. I had a very, very light version of Ubuntu because my computer was such a disaster, and I had this problem. So I think it's something with the graphics or something like that.
Yeah, there must be something. I mean, I apologize, but I don't think I can answer this on the fly. I will keep a note of it and try to send you a message. Okay. After the course. I cannot execute LAMP. You've lied. Yes, I think Isabel might be right. That's the thing, that you need X11, and probably, I mean, this should not affect micrOMEGAs. What I want to show, so, and there is Lorenzo, I can't execute calcap. I only have a calcap.ini file. Lorenzo, did you run make in the micrOMEGAs main directory? And it worked? Yes, the warnings are typically okay. Okay, please bear with me for a moment and let's see if micrOMEGAs will work afterwards. Okay, so there might be some issue which resembles the other ones. I'm not sure actually about this, but let's see. So I guess now you can see I mean, you can see what it looks like on my shared screen, I think. Do you see this gray box that I have on my screen?
Yes.
Yes, okay. So this is the first thing that will open up in principle once you run .-calcap. And so you choose the model, singlet scalar DN. Go to edit model, which is the third option. And there's at the bottom a thingy called check model. This is something which has to do with a strong coupling named in a different way. And then if I press enter again, the model is okay. So this is something which is always a good idea to do if you can, assuming you have X11 and you can actually run a calcap in graphic mode. Basically, it is telling you that there is no gross inconsistency between parameter naming, some syntax error, and so on. It does not, of course, it cannot tell you much about whether your physics is correct, If your model has anomalies, of course, the model might be okay, but this does not mean that the model doesn't have anomalies, but it is at least syntactically okay. So in order...
I'm sorry, could you
Yes.
repeat the last 2-3 steps?
Yes, of course. So I press escape. So yes, you have
Yeah.
variable GG ignored. Press enter,
Okay, yeah.
and then you should have the model is okay. So
I
once
have
again,
a question.
Yes?
Sorry. CalHEP, does it care about the renormalizability of the model?
No, not at all.
Or simply calculate?
It cannot. It does not care about the normalizability. You can actually write down effective Lagrangians.
Cool.
And
Thanks.
this is a very nice. I mean, yeah, I've used this feature. It's actually a nice feature. I think it's a convenient feature.
Yes,
No,
I agree.
so no, CalCep does 3-level calculations, and it treats a Lagrangian at the classical level. So it doesn't know things about normalizability and so on and so forth. Okay. So Pauline, I think you, I guess, yeah, you got variable GG, you press enter, and then the model was okay. And someone asked to repeat the last steps. Is it okay now?
Yeah, it's fine.
Okay, great. So now you can either press escape or just close the window and quit session. Why? Yes. And I will go back to my slides, perhaps for the last time. So the model, most of us hopefully managed to get that the model is okay. And now let's have a look at what the model files look like. So each CalCep model is described by a set of basic files. First of all, and these are the files that you transferred from fine rules to micrOMEGAs, the .mdl files, if you remember. So it has an external library file, which we will not comment because let's not use this today. We're not loading any external libraries. For instance, if you have complicated functions which need to be loaded from external libraries, then yeah, you will need an external library, but this is not our case. Then there's a file called particles1.mdl, which resembles a little bit like this. I've just copied a couple of lines. So you have the name of a particle, in a way that is suitable for you to read, and then how it's called in CalCep, a PDG number, twice the spin, its mass, its width, the color representation. I don't even remember what this auxiliary thingy is, and a LaTeX representation. So these are just a couple of lines. You can open these MDL files if you want and see them and see for yourselves that they actually contain all of the, and I do actually invite you to go into the directory work models and check these files as we speak. Then there is a file that describes the external parameters of the model, so the variables that you actually modify yourself. And if you open the vars1.mdl file, you will see that it looks a bit like this. So the name of your external parameter, its numerical value, and a more human readable description so that you can actually remember what it's about. And then there is a file containing all the vertices of the model. And here I have copied the first couple of lines, which are explanatory, and the simplest vertex, actually. So this is the name of the file, single scalar DM, then it just telling you that these are the vertices, which 4 particles are involved in the vertex. CalCep can handle up to 5 particles, up to 4, sorry, particles. Actually, CalCep can, it can handle up to 4 particles in each vertex. And here you see that we have a Higgs, 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 Higgs. It's a quartic Higgs coupling, actually. What is the factor? And a numerical, if you will, factor, and then a Lorentz part. So the Lorentz part is very simple in this case because it's a 4 scalar interaction, so it's just 1. if you open this Lagrangian1.mdl file, by the way, as I speak, I mean, I'm speaking with reference to my slides, but you can also be playing around in the singlet scalar DM work models directory and opening the files as I'm going through them in order to see for yourselves what exists in each file. So this has a very simple Lorentz part, and there is a factor which is called, in the case of this vertex, for instance, x1, x0. In other vertices, you will see x1, x1, and so on and so forth. So each vertex will have its own factor. And these factors are explained in the last file that comprises our model, which is func1.mdl. And there are two types of functions. So this is the model, this is the file that contains all the internal functions that we talked about previously. I've included two examples in the slides. The first is μss, which is the dark scalar mass parameter, and which we said we will use as not as an external parameter, but we will calculate it from other quantities. So the physical mass of S, the VEV of the Higgs, and the Higgs portal coupling. And secondly, you can also see this x1, x0 coupling factor that we had in our vertex file, in the Lagrangian1.mdl file, and which has a very simple expression, which is -6 lambda. And if you extract the Feynman rules of the standard model, you will see that the quartic-Higgs coupling has this form. Okay. Now, of course, all of this can be written by hand. But if you do open these .mdl files, you will see that they are not, I mean, they can get a little bit cumbersome and the syntax can be a little bit stiff. Whereas in the case of Feynman rules, we were writing in a form which is much, much closer to what we would, to the way in which we would write on a piece of paper. So I personally find it easier to use an external program to generate these .mdl files. In principle, you can edit these .mdl files yourselves and write down your vertices one by one by yourselves, define your particles, define your parameters, and so on. I think that life is made a little bit easier if you use LANHEP or Feynman rules or Sarah. So if you have not done so, I would like to ask you to go to this directory, micrOMEGAs singlet scalar DM work models, and just have a little look at these model files. I will do so myself. I'm not sharing my screen. So as you have a look, as you go through them, I will just like to wait for a few minutes to see if the general idea is clear to everyone. If not, unmute and just ask or send something in the chat. So especially if you open the Lagrangian one, if you look at the Lagrangian.mdl file, you will see many things which appear to be a bit weird. So G of M1 functions, for instance, if you look at line, which one is it, 31, these are gamma matrices. And you will see that in the factor part, there is, for instance, the EE, which is the electric charge, if it's the way we have defined the electric charge, times 28x0, and this you can find x28x0, and this is defined in the func1.mdl file. So if you look then at line 21, you will see some momenta, and this is a normal thing because there are, okay, you want to share? Yes, let me share my terminal window. Oops. Do you see my terminal?
Yes.
Okay. So I'm in this directory here. And I just opened in a generic text editor the .mdl files. Genie is the text editor I'm using, for instance. Yeah, you can use gedit, whichever one you like. So what, is everyone in sync? No complaints in the chat. So yes, let's assume that, let's say that everyone's in sync. If you look at, for instance, at Lagrangian.mdl, Lagrangian1.mdl, and you go to line 1021, you will see that there is the Lorentz part contains a complicated form which includes P1 momenta, that is masses and so on. I mean, this is normal because this example is the photon W plus W minus coupling, which contains derivatives, and fortunately there are some momenta there if you work in momentum space. Okay, so this is one of the basic reasons why I personally never edit a file myself in a CalCap model file directly, but I use tools which can do that. Of course, if worse comes to worse, one must be able to do it by hand. So this is obvious. I mean, we're physicists, we're not programmers. But I mean, if you have quite a few vertices here, we have 70 of them, or 60 something of them. And if you're working even more complex models, then it can become a little bit cumbersome, and there's a high probability of actually missing a sign or something. So, yeah, that is. So, any more questions by browsing a tiny bit through these files, the func file, the .mdl files? Hopefully not. So now we have, I'm going back to my slides for a moment. So now we have created finally, basically our file is ready. And it's kind of time to have, it's almost time to have a bit of fun with micrOMEGAs. It took us a while, but okay. So I will ask you to go 2 folders back into the singlet scalar DM folder. This is the main folder, and run ls just to see what this folder contains. So you will see that it's, among other things, there are two very important files. There's a file which is called main.c, and this is the main file that can be used to tell micrOMEGAs what we wanted to do. So this is the main program that you can edit to select, to tell micrOMEGAs, compute me the relic density, or compute me this or that direct detection cross-section or indirect detection signal, and so on and so forth. And then there is a second file that is called data.par, which can be used to change the external parameter values. So everything that you have in your vars.mdl file can actually also be accessed in real time as you run the program through this data.par file. And in order to run the main program, I would like to ask you to execute these 2 commands. Make main equals main.c. I will share my terminal again, I guess, for convenience. A lot of things should appear, including warnings. Don't be discouraged by that. And then if everyone is ready, so let us run.
Could
Yes?
you just show the command?
Yes, please. Sorry. Can you see it?
Yeah.
Okay, I'm highlighting it as well. Okay. And now it is time, oops, to run this command, /, so execute main, having as an input file data.par. Ready, go. If everything has worked, yay, we have done some physics. So is everyone seeing something like what I'm seeing on in their terminal? If not, please tell me. Okay. Amazingly, yes. Programs work sometimes, not very frequently, but sometimes. Okay. I'm very happy. I'm very glad that this works for at least a few people. Everyone appears to be happy on the chat. So we will discuss your missing files in calcap src lib like numc.a. Okay, this is probably an installation issue. So probably when you first made micrOMEGAs, there was something missing. And amidst the hundreds of warnings, yeah.
But Isabel, you've used the micrOMEGA before.
Sorry?
Isabel has used micrOMEGA before.
Have you, Isabel?
Yeah, like 2 years ago, but now I have a different installation.
Ah, okay, so it's an installation problem. Are you working on, which computer are you working on?
I'm on Mac.
Okay, so on Mac it should work.
Okay.
Did you, and you download it directly from the web page?
Yes. And yesterday I tried to run some other.
Actually, you did run the model yesterday, right? Because you wrote me. Yeah.
And today, yesterday it was working and today is not working again?
Yes.
Okay, in case something happened, let's do the following, Isabel. Let's try the following. Please go, you can see my terminal, right?
Yes.
Okay. Great, Lorenzo. Okay.
But
So
I'm also missing X11, so maybe that's a problem.
I don't think so. Lorenzo, at least it's saying that everything is fine. I needed X11. And to run calcap commands. Okay. Okay, I assume that this has fixed Lorenzo's previous problem. So let's try something, Isabel. Since it was working for you yesterday, run make clean in case something happened today. Yes, remove all generated files. Yes, remove flags for SH and so on. Run a fresh make. Okay, let's go back to the model.
I think maybe my installation, I mean, the end of my installation looks different as yours.
Well, I mean, I'm running Linux and you're
Okay.
running a Mac, so
Different.
that is bound to be different. But I'm a bit surprised that the other.
But do you have an error message when you do make, Isabel?
No, just a lot of warnings.
Okay, so then it should work.
But it's not, it seems. In the singlet, in the pre-installed, let's say, in the existing singlet model, did you get, you got numbers, right?
Yes. Yeah, I think it looked fine.
You're missing files in calcap src lib like numca. Let me check what I have in calcap src. I do have numca. Do you have this file? Probably not, since it's not, it's complaining.
Actually, I do have it.
You do?
Yeah.
Did you, okay, critical question. Did you update something today?
No.
No. So you're not getting any output, right?
Maybe I just try again. Maybe it works now after we reinstalled it.
Any numbers?
So I just try to run make again, like make main equals main.c, and I think it's working.
Oh, okay.
No, so I don't know, maybe.
I
don't know what.
Yeah, I don't know what happened either. So yeah, okay. If you run dots, if you try to rerun ./main.data.par, then hopefully you have an answer. In the meantime, I mean, yeah, if we were in a single room, you would already probably be doing this. But in the meantime, everyone, please, I mean, I am hoping that everyone is going through this output a little bit. It is relatively commented, so you can probably understand a little bit what's going on. Isabel, okay?
I'm not sure. I think I have to follow the steps again and have a look.
Okay, the steps are in, well, actually, now I'm sharing my terminal. Unfortunately, we can share a single screen at a time, I think. And you don't have my slides. So again, this is the command to make, and this is the command to run. If you want, so if it's not running, you please have a look at my terminal, which I'm sharing. Okay. So what you can see here is some of the things that micrOMEGAs can actually calculate for you. It's informing that the dark matter candidate is called ~SS with spin 0 and the mass of, we had just taken by default 10 GeV. the masses and the width of the masses of the Higgs, sorry, and of the various odd particles. So this is the Higgs. So a Higgs in this context is any Z2 even scalar, okay? And then the odd sector particles. It calculated the invisible Z decay actually, and I think it's not excluded, so that's fine. Actually, there is no Z2X in this model. Okay, Isabel's thing is working now. Great. And then you have the calculation of the relic density. And what it is trying to calculate is S plus S going to all even particles, where even includes essentially all of the standard model particles. And then it's informing you that what is the XF? XF is X freeze out. So yesterday in Lara's lecture, you saw the freeze out mechanism, and this is a calculation that is done according to the freeze out picture. We will see later on how to do freeze in actually, and because it's the same model, and this is one of the reasons why I chose it, you can do both freeze out and freeze in. So this is the freeze out X, so M over T. It's about 20, as one would expect. And omega is, there's no check. Sorry, whoops, okay. There's no check that the visible width of Z is small in the experiment. Sorry, there's a control for the Higgs, right? Genevieve, who wrote in the chat actually now.
Yeah, it calculates the width, but it doesn't check.
It doesn't check, okay. So omega H squared is about 0.2 in this case. So it is not 0.12, which it should be, but our first guesses for parameter values were not so bad actually after all. And these are the channels that contribute to dark matter annihilation during freeze out. So SS to BB bar, SS to CC bar, and SS to tau tau. Okay, let's ask a physics question. Why are these three channels? So I have a dark matter mass of 10 GeV. Why are these three channels dominating? Any ideas?
I think because the masses are nearly degenerate, because the bottom and char mass are close to 10 GeV. That's my guess.
And why isn't it SS going into plus E minus?
Because the electron is way lighter than the bottom.
Mm-hmm.
And char.
Which means that its Yukawa is much, much smaller.
Yes, also.
Yeah, I mean, the point is it's not a matter of phase space. The main thing is that, so the process that we are considering is actually SS going through a virtual Higgs into standard model. So on one side of this process, you have the dark matter Higgs coupling. And on the other side, you have the standard model Yukawas. So it is only natural that the particles, so for instance, why don't we have the TT bar? Because dark matter is only 10 GeV. So the channels that you obtain are the ones with the largest Yukawas, actually. Okay. And then there are also some calculations for indirect detection. And this is the sigma V at V tending to 0 in units, in the usual units that are used in indirect detection, centimeter cube over second. The main contributing processes. And then, I mean, various more quantities. So the photon flux for an angle of 0.1 radians, and so within a cone of angle 0.1 radians. The photon flux within this cone for 5 GeV, the positron flux at 5 GeV, the antiproton flux at 5 GeV. So you can see that the program can actually calculate quite a few things for you. Then you have the cold dark matter nucleon amplitudes, taking into account different process. I mean, in this case, it's actually dominated by Higgs exchange, the wind nucleon scattering, and you get a spin-independent cross-section for dark matter, for scattering of protons. I hope you can see what I'm highlighting with my cursor. Yes?
Yes.
Okay, great.
Yes.
The anti-WIMP the anti-WIMP proton spin-independent scattering. I mean, of course, in this case, matter and antimatter are the same, but you can have a model of non-self-conjugate dark matter in which actually you have different scattering rates between matter, between nucleons and matter and antimatter. And then spin-dependent, the same for spin-dependent, matter and antimatter. In this case, everything is scalar. There is no spin-dependent scattering. And the same things for spin-independent scattering of dark matter or dark antimatter of neutrons and spin-dependent scattering. These are actually the amplitudes, and below that you can see the cross sections, which, since they're in picobarns, I mean, as you might understand, are very severely excluded, which is consistent because frozen out dark matter in the singlet scalar model has been excluded since many, many, many years in this minimal framework from direct detection. So then there is also a check that is telling you that, I mean, this is comparing with 2018 xenon data, and it's heavily, heavily excluded. Finally, what you have is the Higgs width. Yes, finally. And gauge boson decays. So, so these are the things basically. I mean, okay, let's not go through them in detail. Higgs to SS. So you have an invisible Higgs width predicted in this model. It makes sense. And then all of the rest of the branchings of the Higgs and the gauge boson. So these are the things that once you write the /mu model command, you have a default main.c program that is created for you. And if you run this default main program, this is what is calculated. There are more things that one can calculate. But first of all, let's go play with our parameters a little bit. So I would like to ask you to open the data.par file. So and to change, so this is empty. It should be empty for everyone. And this means that we have not changed the value of any parameter. We have just used whatever default values we have given our parameters in the beginning. So I'm going back to my slides. I would like to ask you to change the values of some parameters. And for instance, we had given a value of 0.1 to our coupling. Please change it, for instance, to 0.16. And then you can also change the mass. I mean, do these two changes consecutively. First, change the coupling, and then also change the mass. Before and run once again /main data.par. So if I am increasing, let's do a little bit of a quiz. If I increase lambda SSH from 0.1 to 0.16, what will happen to the relic? What do you expect to happen to the relic density? Any ideas?
It should reduce.
Yes. Is this what you find?
Yep, it reduces.
Okay, great. And then so you can add, So basically in data.par, whichever variables are mentioned, they are assigned the values that you assign to them. And whichever variables are not mentioned, just keep their default values that are in the .mdl file, vars1.mdl files that we have in work models. So if you add MSS 300, so if you increase the dark matter mass by a lot to 300 GeV, what do you expect to happen? Or you can even run the program, see what happens, and then try to understand why this is happening. Any comments, interventions?
There is a top channel now.
Yes, that's it. So it decreases even more because now we have opened up an annihilation channel with an extremely strong coupling, an extremely strong Yukawa coupling, and this means that the predicted relic density actually plummets. Okay. So hopefully, is everyone on the same page? Has it run for everyone? Everyone saw these effects? Omega changed as it should and everything. If someone is having an issue, please do say it in the chat. Okay, so since no one appears to have an issue, let's go to the main.c file now, which is the main file that you're editing in order to modify what you are asking micrOMEGAs to do and so on. And I think that the best is to actually open your main.c file. And we can start going through a little bit what is being done there. So this is a C program. I hope everyone has some familiarity with C. So the general structure, so I'm sharing my slides, not my text editor. So you can actually have a little bit of a scheme of what's going on in this main.c file. And hopefully you can find the various parts a little bit by yourself. So first, you have some switches to turn on and off certain modules, so certain functionalities. For instance, define masses, the functionality define masses, functionality masses info is switched on in this case. It's uncommented, and this displays information about the mass spectrum. If you go back to your terminal, you will see that at the very beginning of the output, we had masses of Higgs and odd particles. This is where this module is where this came from. Then you have constraints. This is an uncommented module, but everything it basically would amount to is essentially commented. So, I mean, you can uncomment in order to apply constraints from monojet searches at LHC, Higgs bounds, Higgs signals, Lilith, models, and so on. Your best friend when you run micrOMEGAs is the next one. So this is the functionality which allows you to calculate the freeze out abundance in your dark matter model. I'll be checking also the chat in case there are any questions. Hopefully there are not. Genevieve said that, yes, there is a check of Z2, invisible in constraints. Yes, that's what I thought. Then you have modules to calculate things for indirect detection. Reset form factors concerns the direct detection. You know, you can change your nuclear form factors essentially. And then CDM nucleon is for calculating the WIMP nucleon scattering cross section. CDM nucleus is to calculate exclusion bounds from direct detection. And decays is if you want to calculate decays decay widths and branching ratios of particles. So this is the first part of your main.c, you choose, I mean, there are more switches which you can turn on and off. For a full account, I would like to invite you to consult the micrOMEGAs manual. You can turn on and off certain modules. The fact that some of them are turned on does not mean that they will be used in that they have to be used in the following. But if you want to use a functionality, you have to switch on the corresponding module. Then there is a series of, so then our main program starts at int main and so on and so forth, etc., etc. This is just a small routine to read the data.par file and to perform various checks. So since we're going on through a rather lengthy file, I would like you to stop me if at any point you're lost. Okay, just unmute and tell me I'm lost, and we'll slow down. Then there is one very important command which is called sort odd particles CDM name. What this does, so this is a command that needs to be run essentially every time that you run micrOMEGAs. This is a command that if you have any calculations for a particle spectrum, any relations between masses, any whatever, every time you change your parameter from within the main program, you have to run this command, and it assigns all the masses and it sorts all the Z2 odd particles by increasing mass. Essentially, this is the command that finds which one's your dark matter candidate. Because if I had S1 and S2 and one of them was lighter, this command will tell me which one is lighter. And its name, which will be CDM1, and if there is a second dark matter candidate, there's also going to be CDM2, are written in a record, a text record, which is called CDM name. Then there is the command a little bit below that, Q numbers. So this is a generic program that is written having two dark matter candidates in mind. One can simplify greatly this program. And in this case, we only have one dark matter candidate. Q numbers, which returns the quantum numbers of your dark matter candidate or candidates. And then there are the various modules which compute different quantities, such as the relic density, the dark matter nucleus scattering cross-section, plotting, etc. This file, of course, you can edit. For instance, if I can just delete the if depth masses info part, and if I rerun my program, I will not have the mass information at the top of my output. And so, as I said, today we're only going through a few of these functionalities, and for a full account, you can check the micrOMEGAs manual. Since the main program is actually quite lengthy, I mean, first of all, please do have a look at what's going on here. And I would suggest to actually move to a simpler program because we have only 15 minutes left. So if you follow the preparation instructions, normally you also have a file which is called mymain.c. And I would like to ask you to place it in the singlet scalar DM folder and open it. Whoops. And I was going to leave this as an exercise, but I don't think that we have time to write it from scratch. So we can edit this kind of simpler program and use it as a guide for also more complicated cases. Oops. Giga's micrOMEGAs has crashed. I guess with playing I did something wrong, and make is no more working. I would meet you. Okay. Yes, Giga, let's meet in Gather Town. In the meantime, you can go to the main folder, try to run make clean, then run make, then go back to the singlet scalar DM folder and repeat the steps to remake your main file. Okay, is everyone seeing the mymain.c file? Has everyone opened it, not seeing it? Yeah. I hope yes. So this is a greatly simplified version of the main file that micrOMEGAs generates by default once you create a new model. What this little program aims to do is what you can see in the slide. So first of all, change the values of the dark matter mass and its coupling from within the code. This is a useful thing to do because if you're running a scan, for instance, you might not want to write and rewrite external parameter files all the time. You might just want to run a script that changes the value of some parameter. This can be done with the command assign val_w, which you can find at the, so if you do have mymain.c open, there is this little thing saying play with parameter values. And there you can change the mass and the coupling of dark matter. The second thing that this program does is to compute the freeze out dark matter abundance and print the contribution of the main annihilation channels. This is achieved where I have written freeze out scenario dark matter abundance by the command dark_omega. This is the main freeze out command in micrOMEGAs. It also exists in a variety where it can treat two dark matter candidates. And print channels is so it also returns a freeze out temperature, which is XF. Fast and BFs have to do with the accuracy and the method that is used to solve the Boltzmann equation. And error is just an error flag, which in order to be able to see what went wrong if something goes wrong or if something went, or if everything went fine. And print channels actually prints information about the various things that, which channels contribute to dark matter annihilation. And also the freeze out X, and it only prints, if I remember well, the channels which contribute more than what you define by this cut variable. So in this case, cut is 1%. The next thing that is done, that this program does, is to calculate the spin-independent and spin-dependent wind proton-neutron scattering cross-section. So what is going on in the module that you see, the CDM nucleon, a little bit before that, is that you have a function which is called nucleon amplitudes. It will calculate the wind nucleon scattering amplitudes for the particle CDM1. So CDM1 is our dark matter candidates. It was an output of sort-ordered particles which we wrote down at the beginning of the program. And it returns the spin-independent PA0 and spin-dependent and PA5 matrix elements for matter, dark matter and dark antimatter for scattering against protons. So this is the P, and neutrons, this is N. And then SCOF just below it is just some prefactors when you want to pass from the amplitude level to the cross-section level. And basically what this will do is to calculate, to multiply, so this program just multiplies this numerical coefficient with the amplitudes and it spits out the answer. So see, these ones are cross-section for spin-independent scattering of protons, spin-dependent scattering of protons, spin-independent scattering of neutrons, and spin-dependent scattering of neutrons. So let's start by running the program as it stands. So I remind you, make main equals mymain.c this time. So you see that, of course, you can write down your main program as you wish and call it whatever you want. And now you should have a mymain executable, which you can execute with /mymain. And you get a much more restricted output with only the few things that we asked micrOMEGAs to do. And you can see that the coupling was chosen more or less to reproduce the correct dark matter abundance of the universe. It's 0.13 in this case. Did it work for everyone? I don't see complaints in the chat. You can just also unmute and speak up. Is it okay that the program says MSS not found and LAM SSH not found? It really says that for you? So let me change my share. So your output is not like this.
Sorry, Lorenzo, what did you try to do to get this message? Did you try to change the mass parameter in the data file, or what did you try to do?
MSS not found. Wait, okay. Have you run, you reinstalled something? Or did you make something again, erase something? Okay, if you open the you only combine my main.c.
Then you did my main with some input data file.
Yeah, what did you run after my main.c? After you compiled my main.c? Okay. And so did you change data.par before and run it, as we had said, when we were running the main.c program?
Shouldn't .mymain have then a data.par like input for that
No,
command?
that is the point. That is the main thing that, no, the thing is that, sorry, just to reply to Lorenzo first. This probably means that, I mean, there is something wrong with your micrOMEGAS installation probably, because if you had modified the data.par, we did the exact same thing of modifying these parameters from the data.par file. To answer the question that was just posed, no, you don't have to have an input file. This is one of the goals of this exercise, if you will, that I mean, if you look at the main file, there is in the beginning this whole part to read the input file and so on and so forth, and to print out error messages and break if the input file is not provided. But in this case, no such thing is done. You can just write micrOMEGAs without external input files, just by changing your parameters through this assign val w command. You just need to modify. So if you want to, and I do advise you to do this, if you want rather to write your main file by relying on the main.c file that is generated, you can just, I mean, that's what I did. I just removed all the first part with the reading of the data.par, and I edited, and I created this my main.c. One almost always starts with, I mean, this is why the main.c file contains so many different functions and so much of the information, because it's easier to subtract things than to add things, if you will. Okay. So the answer is no, you don't need to provide for my main an input file. For main, the way it's written, yes, you do need to provide an input file.
Okay. Yeah.
Okay.
Yeah.
So in the 2 minutes that we have left, I would like to ask you to do one last modification, just to exemplify a relatively recent feature of micrOMEGAs, which is freeze-in. And I would like you to uncomment the commands that you can find at the end of my main.c. down to endif. So the assign val_w command, the air flag for shorter particles, Q numbers, and everything in ifdef freeze-in. So what we can anyone take a? I mean, okay, it's written in the slides also, but I think I don't even remember what I'm sharing at the moment. I'm sharing my text editor, I think. Can anyone? Sorry.
You're sharing the terminal.
The terminal. Okay, great, even better. Can anyone take a guess as to what I'm trying to do here? I mean, from what's written, you can probably guess that I am trying to also calculate the dark matter abundance in the freeze-in scenario. Under the assumption of freeze-in, actually. Why am I reassigning the values of, why am I redefining the value of the coupling? Any guesses?
For freeze-in mechanism, we require the coupling to be really small.
Mm-hmm. Yes, that is the reason. So if you rerun, now that you have uncommented these lines, if you repeat the same process, if you make again your main, my main.c, and rerun it, you'll see that lots of things are happening. A few more things are happening, and I'm getting a second relic density, which is a relic density from freeze-in, and it's all, again, more or less tuned to be the correct value. Here, let's go back to my main.c. The main commands that were used here are dark_omega_fi, tr air. So what this command does is that it calculates the dark matter abundance in the universe according to freeze-in mechanism, assuming a reheating temperature Tr, for taking into account all scattering processes, I mean, based on 2-2 scattering, taking into account all scattering and decay processes that can contribute to dark matter production. Okay. And then, just for fun, I'm also calculating, there is another command that you can use, dark_omega_fi decay, in which you specify, once again, a reheating temperature. In this case, I've taken it to be 10 to the 10 GeV, so really, really high. From the decays of a single particle, H in this case, And if you go back to your terminal and have a look, you will see that actually the two numbers are very, very close. They're essentially identical. So omega freezing taking into account everything, and omega freezing taking into account Higgs decays are equal. What is this telling you? It is basically telling you that the main contribution of all the processes that contribute to dark matter reduction is Higgs decay. Okay. So this is basically what's bringing us to more or less the end of today's tutorial. I want to make a last comment. What would happen if I had not changed in my main.c if I had not included the second assign val w in order to assign a feeble value to lambda SSH? What would have happened is that I would obtain an enormous relic abundance. And going back for one last time to my slides, I want to point out this thing, that micrOMEGAs, no matter which values you choose to give your parameters, micrOMEGAs will provide an answer, a numerical answer for you. If you try to insert a feeble value for your couplings and then run a freeze out command, be it in micrOMEGAs, be it in darkSUSY, be in whichever program you want, you will get a numerical answer. It will be, however, a wrong answer, because you will have violated, quite likely, chemical equilibrium in the early universe. If you try to compute freeze-in abundance, the freeze-in abundance in micrOMEGAs, only micrOMEGAs is a public code to calculate freeze-in actually at the moment, at least to the best of my knowledge. With a wimpy coupling, you will still get a numerical answer. It's an inconsistent answer, though. It's a wrong answer because you're assuming that there is no chemical equilibrium, whereas one would expect that with such a coupling, there would be chemical equilibrium. So micrOMEGAs does not check whether freeze-out, freeze-in conditions apply. Right, as Michael is writing, if you recomment rather the reassignment, omega is 10 to the 20. So it's a ridiculously large number, and it's not even a correct number. That's the point, because this is a freeze-in calculation with a wimpy coupling. This is an inconsistent thing to do. So this means that you do need, and this is not just the case for micrOMEGAs, it's the case for every dark matter code and every code, some knowledge of what you are doing. Okay. And this brings me a little bit to a few elements of summary and some final comments. So micrOMEGAs is a computer program that allows you to compute the dark matter abundance of the universe along with other observables in general extensions of the standard model of particle physics. Today, we only had the possibility to scratch the surface of this. You're invited to consult the manual to explore all the possibilities that micrOMEGAs can give you. This can be found, there's a dedicated directory man in the main micrOMEGAs directory. There are other dark matter codes such as darkSUSY. You'll hear about that tomorrow by Thorsten Brinkmann and MattDM. And this is a very good thing, actually, because this allows us to perform comparisons between different codes. It provides versatility. And every code has its quirks. Every code has its advantages and disadvantages, and its specialized features. So additional, even more specialized tasks can be performed by other codes. So for instance, if you want a full-blown and more sophisticated cosmic ray propagation routine, you can use stuff like Dragon and programs like Dragon and so on. Two of the strongest points of micrOMEGAs are, in my view, first of all, its capability to implement new models without modifying the core of the code. So again, you can just implement your new model by importing model files and running new project. This is a feature which is also shared by MattDM. These are the only two codes that can do this. And the possibility to compute the freezing dark matter abundance. And this is actually unique for micrOMEGAs as far as public codes go. And there are many ideas of how to further expand the codes. And this also depends on what the community at large keeps asking. So yeah, thanks.
Thank you very much, Andreas. There is a quick question in the chat.
Is it possible to plot the typical freeze-out relic abundance versus temperature? Yes, actually it is. If you look at the, I don't have the command now under my eyes, but if you look at the manual, there are plotting commands. So you can actually do that. And you can export it in Python and other formats if you want. Okay. Okay. Are the slides available somewhere? Not for the moment, but they should. So how do I do this? I don't know where I should upload them.
Well, you can always have a look at the videos on the YouTube channel regarding the slides. Maybe we can make them accessible.
Maybe it's a good idea, because especially for the tutorials, maybe it's a bit useful because the commands are in there, and if someone wants to rerun them, yeah.
Okay.
I'll send them to the organizers, and the organizers will take care of that, I think.
We will let you know.
Okay, great.
Actually, if I can comment, we are collecting all the slides, all the talks. So
great,
yes, we'll be probably asking you about
okay,
that.
Cool, great.
Thank you so much.
Thank you.
So thank you very much, Andreas and Geneviève as well, for this very nice hands-on session that triggered many questions. Since we are running a bit late already, I suggest that we actually go to the Gather Town meeting, and then you can ask all the questions you want to Andreas and to all the speakers of the day.
Yes, I'll be in room 5 in 5 minutes. Or so.
All right.
Okay.
Perfect. Thanks, everyone. So let's meet on Gather Town. Thanks.
Bye.